All right, today we finished our discussion of the flat plate boundary layer, and we picked up from where we were in our last lecture where we talked about the laminar cases. Just to be clear about the things that we're interested in describing the boundary layer, if we have a velocity that's approaching here v0, the boundary layer height is defined by delta of x. The shear stress on the plate is defined as tau of x, and then we can integrate tau of x to define a total shear force, which is the area integral of tau over the entire flat plate. But we're going to write this as a friction coefficient times 1/2 rho v0 squared times the surface area of the plate, so the width times the length. The friction coefficient of the plate is a function of the Reynolds number based on the length of the plate, as well as the roughness. So Ks over L, the roughness, in the same way that we had roughness for pipes. Now, I guess in the figure I'm going to use here, they use epsilon instead of Ks. But I provided a summary of how delta and tau vary for the turbulent cases. I would refer you to the class notes for that. All I want to really emphasize here is with regards to the flat plate drag force as a whole, the friction coefficient appears graphically as a function of the plate Reynolds number here. And the laminar regime is this early part up to a Reynolds number of 500,000. It then undergoes a transition to turbulence following this curve, and eventually asymptotes to this line as if it was a fully turbulent plate. Now that's a smooth plate. Notice that as we consider rough plates, the drag coefficient increases and becomes strongly a function of roughness and less a function of Reynolds number. Now the last thing I'll mention with regards to this curve is to think about the segments of the curve that lie beyond the transition or before the asymptote. So this first one, this is a case where the plate remains laminar beyond the threshold, so it does not transition. That is an occurrence that can occur, but is not frequent. Generally, it will transition naturally at around 500,000. The more interesting part of the curve here is this one that has it continues the turbulent curve back to lower Reynolds numbers, and that would be the tripped turbulent boundary layer. By tripped, we mean that it's forced to be turbulent from the start at, say, x equals 0. And so you're along this curve that I'll highlight it in red now, that continues smoothly throughout Reynolds number space, and in some ways that makes it more predictable than if you rely on this transition to turbulent. All right, so this figure basically allows you to, for a given plate configuration, for a given velocity, establish the friction coefficient. From that you can do the total force.